Hello everyone, my name is Yash Dikshit. So I did my BTech in Electronics and Communication, and currently I'm working as a VLSI engineer in one of the best semiconductor industry. Okay, so I'm your tutor for this course, Static Timing Analysis, and I'm going to start with this course with a different modules. Okay, so basically I'm dividing this course in different kind of a module. So might be there can be around 10 modules, 11 modules. So it will depend on the course content. So when the time is passing, I will decide like how many modules are sufficient for discussing the static timing analysis course. Okay, so okay, so let's get started with this course. So see, if you have some questions like why you need to study this static timing analysis. Okay, so there shall be so many questions. Okay, but let me tell you one thing, the timing is very important portion when it comes to chip designing. Okay, so you already know that there is a trade-off between power, area and timing, right? Performance, that we can say. So might be you can compromise with power, might be you can compromise with area also. Okay, but you can't compromise with timing. Okay, because timing is very important. If suppose timing is going to be degraded, okay, so in that case your functionality is going to be degraded. Okay, why I'm saying that if the timing is not good, then in that case that functionality is going to degrade. So everything you should get a clear picture when you are going through with this static timing analysis module. Okay, so what are the course content, like what are the objective of this course? Okay, so the people who are targeting for VLSI industry, who want to work in the digital domain, or there are so many different profiles. Okay, so static timing analysis is a basic need, and you should know the concept of static timing analysis. Okay, so see, the static timing analysis is not all about the setup and hold time. Okay, there are so many concepts that you need to understand. Why I'm saying that you need to understand, because when you are going to do the timing analysis on tool, okay, so tool don't know that there is a AND gate, there is a NAND gate. Okay, so there are some properties that you should need to understand. Okay, so if you get a clear idea like what is the backend thing is happening inside that tool, okay, so your understanding is going to be improved in that case, right? So why these conceptual topics are very important, because you are going to your debugging skills must be good, right? So what are the content that I'm going to cover in this course? So you see, there are different contents, like I'm going to cover what is a STA. Okay, there is different topic DTA. Okay, so what is the difference between STA and DTA? That both the topics I'm going to cover. So you shall we have like so many questions, like while studying this course, why we are not using DTA, why only the static timing analysis? So you see that in the industry also we have profile called static timing analysis, why we are not using the DTA? So these many questions, the question will be answered in this course. So just have a patient and just go with me, along with me. Okay, so we'll start with the very basics STA part, then we will cover digital timing concepts, because when we starting with the STA, there are different terminologies that you need to understand. Okay, because those terminologies are very important, because I'm going to use in the later part. Okay, so if you know the proper definition, proper graph, okay, the graph part of that, so if you have a clear quality of that thing, then your concept should be clean. Okay, so one thing I should like comment on that, always focus on your basics, don't try to learn any definitions and all. Okay, so we will start from the very basic and don't worry about that. Okay, so we will be seeing this digital timing concepts also. Okay, then we are going to see the delay concepts also. There are delay concepts, like how we are calculating the delay of the digital circuits. Okay, so we will understand how the calculation of delay is going to be happen. Then the other thing is like cell delay, net delay. Okay, so in the digital circuit there are total two different things, right? One is like you have a gates and all, right? And basically suppose you have a two gates. Okay, so that two gates are going to be connected using that net. Okay, net, okay, wire. Okay, so that delay also counts, right? So what is the cell delay? That delay of that particular standard cell, like AND gate and all. And what is the net delay, how we are calculating that thing? Okay, so both the things we will study, and then we will see that what are the timing arcs. Okay, so timings are arcs, like it's very important, and from here like I will start this course basically from timing arcs. Okay, so these are the very important topics, because when you understand the timing arcs, then I will jump to the unit nest, because these are the properties that is going to define the functionality. Okay, so basically in the .lib file, okay, that's called the library files. Okay, so the timing library files, right? So in that there is a like everything is mentioned. Okay, so how the tool is going to see whether it's a AND gate, NAND gate, what is, because for the tool, suppose let me give you one example. Okay, one thing, let me give you one example. Okay, so suppose you have a 2 gate. Okay, so suppose you have a 2 gate. Okay, so suppose you have a 2 gates. Okay, so for tool it is act like this. Okay, so suppose here we have a AND gate. Okay, but for tool this is a black box. Okay, so what is it? It is a black box. Okay, so what is it for the tool? It is a black box. Okay, so for tool it is a black box. Okay, so what I'm mean to say from the black box, so tool don't know whether it is a AND gate, whether it is an NAND gate. Okay, so how the tool is going to understand in that scenario? Okay, so there are some functionality, the properties and all, like we will going through in the static timing analysis course, so just wait for that time. Okay, then we will discuss about setup and hold time, so most important topic. Okay, so basically when it comes to STA, most of the people think like it's all about static timing analysis, all about like hold time and setup time. Okay, but that is not the case, right? So static timing analysis is not about the hold and setup time. Okay, although we need to fix this thing, this is the major thing, like when you are running on the STA tool, so this thing we need to fix, right? But there are some important topics that we need to understand, how we are calculating the delay of the circuit, right? So that is a very important. Then if you know the calculation of delay, okay, you know the basic concept, you know the everything in that static timing analysis, then the setup time and hold time will be like very easier for you. Okay, and we will be discussing some other important concepts also. Okay, so this is all about the course content that we are going to see in this course. Okay, so now let's get started with this course. So I will be covering all these topics, and before going through these topics, I will provide you some basic thing also, that like basic CMOS concepts that are very important. Okay, because if you don't know those basic concepts, might be in future you will be stuck in that, right? So if I am teaching your STA, then I'm not going to refer anything like you can refer this thing from somewhere. No. Okay, so if any functionality is coming, I will explain. Okay, so these are the basic course, like basic module I'm going to cover. And this I will be discussing about the CMOS concept. That's a very important, right? So it's kind of a revision for you also. Okay, so let's get started with this course. So this is the introduction part. So what we are going to cover in this module 1. So these are the topics that I'm going to cover in the module 1. Okay, so see, without further delay, I'm going to start this thing. Okay, so see, when you're going to study anything, there are some prerequisite, like there are some topics that you need to understand, right? Because suppose if I'm going to teach you the definition, right, so that is not going to help you, right? So what is my intentions, like when I'm going to teach this course to you, just think. Okay, so nothing you need to remember. Okay, just think. And if your digital fundamentals are very good, then you will definitely going to enjoy this course. Okay, so I will cover some basic concepts also that are very important. Okay, so every VLSI engineer should know that topics, right? So these are the topics that I'm going to cover in this. Okay, so what I will be covering in this, or what is a STA, I will start with the definition, like what is the STA. Okay, then I will start with this digital design basics. Okay, so what does it mean by the digital design basics? So there are some topics that I will explain to you. Okay, so after that I will also discuss about this what is the difference between this STA and DTA. Okay, so this question is very important. Okay, this is one kind of a question also. Why? Because if you are studying STA, then you should know what is this pros, what is its cons. Okay, why I'm only studying ST only, why I'm not going to for the DT. Okay, so these timing concepts, if you think like deeply, then you will get a very good command on these topics. Okay, so we will covering this difference between STA and DTA. Then we will be covering different terminologies that we are using in STA. This is a very important. Okay, so this is a very important because in this I'm going to start with the terminologies that we are using in the static timing analysis world. Okay, so let's get started with this. So you have further like studied anywhere, okay, you have heard about STA or static timing analysis. Okay, so if you don't know, then it is fine. Okay, so let me give you one scenario. Okay, so suppose you have a any digital circuit. Okay, so suppose you have a digital circuits. Let me draw one circuit. Okay, so suppose you have any digital circuit. Okay, so there will be like multiple gates. Okay, suppose second input is coming B, it's A. Okay, and suppose it's have to A dash, second input is B dash, and here we are getting this output. Okay, here we are getting this output. Okay, so this is a one general diagram. Okay, so suppose now the signal, suppose if we apply any like any value, suppose if you are applying A dash is equal to 0 and B dash is equal to 0. Okay, so this is the AND gate, and output should be 0 only. Okay, so this 0 I'm applying on this input for the second gate. Okay, so when this 0 input is applied at A dash, what exactly time it's reached to this output of this AND gate? Okay, so you understand what I'm saying. So the data is going to be traveled. Okay, how much time that it takes, like whatever the time like it takes to deliver that output, right? So these are the things, right? So suppose if you have any start point, if you have any end point. Okay, so suppose this is the input pin and you are getting output from here. Okay, so might be there are like suppose 20 digital circuits are there, like AND gate, NAND gate. Okay, it's a combination. Okay, so how much time after you are getting this when you applying the input, how much time it take to reach to the output? Okay, so there will be some particular time now. So how are we going to calculate these things? So these things related to with the timings things. Okay, because data should be stable also, there will be some concepts related to data. Okay, because it's all about data, because data is only flowing in this system. Okay, so to calculate this thing, this timing things, we have a concept of STA. Okay, so what is a STA? You can see in the definition. So STA is a method of validating the timing performance of a design by checking all possible paths. Okay, so what does it mean? Suppose if you have any digital circuits, okay, there will be say 50 gates, 20 gates, might be 100 gates. Okay, so there will be different kind of paths. Okay, there will be like multiple paths are there. Okay, so it will validate all the timing paths. Okay, design. Okay, and it will check any timing violation is there, and it will calculate the timing for that thing. Okay, so how this STA is working? So suppose if you have a big design. Okay, so you are just breaking your big design is into a small module. Okay, so that in the STA terms, what we call it as, it will be called as timing paths. Okay, so what are these terminologies? I will explain you later. You will get to understand like each and everything. Okay, so don't worry about these terminologies. Okay, so you got to know why we are using STA. So STA is just like a calculation of a timing. Okay, so if circuits are there, if you apply any input, then how much time it will take to reach to the output. Okay, so it's validating the timing. Okay, so if suppose if you have a constraint, like suppose you have a 20 gates. Okay, if you apply input at A, okay, then it should be reached at output Y. Okay, if you have like constraint like it will reach minimum 7 picosecond. Okay, if suppose if it is not reaching in 7 picosecond, if it is taking 8 picosecond, that means your timing is validated. You need to fix in that case. Okay, so these all things we need to do with it STA. Okay, so now you can read the definition that static timing analysis is the method of validating the timing performance of a design by checking all possible paths for timing violations. Okay, so how does STA works? STA breaks a design into timing paths. Okay, so there are different timing paths. I will discuss these things in the later videos. Okay, so calculate the signal propagation delay along each path. Okay, so basically if suppose you have a two gates, okay, I'm just considering very small example to understand, okay, for the understanding purpose. So suppose if you have a two gates, if you are applying any input A, then it should reach at the output of Y. Okay, so that means if you are applying input at A, you are getting output Y. Okay, there are between two gates. Okay, so how much time it is taking? Okay, so it's called as like a propagation delay terms, right? So we will calculate this propagation delay, then we are getting actual delay of that circuit. Okay, and checks for violations of timing constraint center design at input and output interface. Okay, so we are checking whether any violation is there or not. Okay, so this is all about STA. So now you get a better idea, like, okay, now you get a basic idea why we are using STA. So we are calculating the delay of the circuit. Okay, so for the delay calculation, okay, so that we can assure you that there will be no timing violations. Okay, so just because of that we are using this STA. Okay, so now one question is clear for you, that why we are using STA. What is a STA? Static timing analysis. Now see, if you see this word static timing analysis, okay, so see this word static, you can easily see what does this word mean. Static means we have a two words, static and dynamic. Okay, so static means that is fixed, right? You don't have to define anything. So what is the difference between STA and DTA? So static timing analysis, you don't have any like input vectors. Okay, so suppose for two input AND gate, okay, how many inputs are possible? 0 0 0 1 1 0 1 1. So there will be like 4 combination. Okay, so if we are applying, if we are testing this timing for this circuit, okay, so if we are testing, like if we are applying inputs like AA for like AB like 0 0, then we are calculating the time. Okay, then applying for second vector, third vector, fourth combination. Okay, so that means it is taking little bit time, so it is dependent on the input vectors. Okay, suppose if we have a long very big circuits, then it is not feasible, right? We can't calculate this for all input vectors, right? So because there will be lots of combination. Okay, so it's practically it's not possible. Okay, so that means like it's happening in the dynamic things. So dynamic timing analysis, we have a input kind of vectors. Okay, so now you understand what is the difference between ST and DTA. So in the static timing analysis, it will not consider the input vectors. Okay, it will calculate the timing for all the paths. Okay, inside that false path also consider, every path will be considered in this. Okay, static timing analysis. So basically what is ST like? It will calculate the worst delay. Worst delay means suppose if you have a place A, you have a place B. Okay, and if you want to reach from place A to place B, okay, so suppose you have a time frame like 5 seconds, like suppose 5 minutes. Okay, so if you reach in 5 minutes there, okay, so if suppose if you are reaching 2 minutes, 3 minutes, 4 minutes, 5 minutes, up to 5 it's fine, right? But you need to consider all the worst scenario, right? Because might be this will also happen, this will happen. So the delay, we take it in the terms of the worst delay. Okay, so we calculate the worst delay in this static timing analysis. So these are the concepts, like you should be familiar, like you will go through when we are proceeding in this case, like in this course. All doubts must be clear for you. Okay, so now you got a very clear picture what is a STA, why we are using this, what is a DTA. Okay, so now next now if you get to know that what is a STA, so here is the comparison of STA and DTA. Okay, so you see in the circuits we have a flip-flops, right? So there are synchronous, right? So suppose if any clock is, what is a synchronous circuits? That clock source, that clock we are applying, it is common to all the flip-flops. Okay, so that is a basic thing. So what is the STA like? It's what are the advantage of this? Now you easily understand this thing. Okay, it's a fast, exhaustive, no stimulus required. As I told you, there is no input vectors we are setting here. Okay, it is a fast. Okay, so you can't so suppose any circuit you delay that you are calculating, it is not depends on the input, right? So if it is not depend on the input, your time will be saved. So it is a fast way of method, like fast method calculation. Okay, in the DTA, what is it is a slow, because it becomes like non-exhaustive. Why? Because there we are applying input vectors, right? So that's the basic difference between STA and DTA. Okay, but in the STA, suppose we are just taking the worst worst case delay, right? So it's a less accurate, okay, can report false error also, okay. But suppose in the DTA you're applying 00011011, so you have a you're calculating that timing with respect to the inputs, so that means it is a very accurate, okay. So that is a advantage for the DTA, okay. Another thing, like for STA, it is done only on the synchronous part of a design. So what is the synchronous part? The clock source is common, okay. So suppose if we have 100 of flip-flops in our design, in our chip, so that means the clock source is a common for that, okay. But DTA, as I said, it depends on the input vectors, okay. So in the STA, another difference is like can't detect timing errors related to the logic operation, okay. So see, STA doesn't check the logic, okay, don't check the logic operation, means logical connection of this gate, whether that AND gate is working fine, whether that NAND gate is working fine. So STA is not all about the functionality, is only just calculating the timing things, okay. But when in the DTA, suppose if you are applying that 00 input, then output should be for AND gate it is 0. So in that case, it's checking the functionality also. So that is the advantage for DTA. So DTA, it checks functionality of a circuit also, okay. So now we will see some important digital CMOS VLSI basics, okay. So you will be you will be wondering why I'm this like talking about this, why I'm not coming directly to the ST, okay. So see, what is my intention is like these topics, understanding of these topics is very important, okay. So I will give you some idea, some important points for these topics, because you have a crystal clarity in your mind, okay, crystal clarity in your mind, so that you will not face any doubt, okay. Don't like any doubt, you would not face any kind of, okay. So that's why I'm covering this kind of a topics, okay, because you're already familiar with these topics, okay. But I will add you some points here, you can just relate these points, but you can recap also, okay. So that's why I'm covering this thing. So I will be covering these 4 points, okay. I will be teaching you like what is the CMOS, then how to implement any logic, okay, using CMOS, okay. You already know this thing, right? That what is the logic 0 and logic 1, and some CMOS important concepts, okay. So these points I'm going to discuss, okay. So now you're already familiar with the CMOS things, right? So what is a CMOS? So it is a CMOS means like complementary metal oxide semiconductor, okay. So here in the right side you can see this is a CMOS inverter diagram, okay. This is a CMOS inverter diagram. So this part is a PMOS, this is a NMOS. So you are already familiar with this thing, right? So here gate are shorted and it's connected with the input, okay, and we are getting this output from this Vout, okay. So this is the drain of both, this is a drain of PMOS also and drain of NMOS also. This is a source, and here at the top this is a source, okay. So this is a source. So current will flow from source to drain in PMOS and drain to source on NMOS, okay. So these topics, these terms you already know, okay. So you already know like this is a CMOS complementary metal oxide semiconductor. Why I'm calling this is a like CMOS as a complementary metal oxide? Because see, any logic that we are creating using CMOS, so we have a 2 main points, okay. So how the logic is going to be constructed? So basically we have a pull down network, we have a pull up network, okay. So pull up network is connecting to the VDD, and that pull down network is connected with the ground, okay. Why it is calling as a pull down? Because it is going to pull down your output to the ground, okay. So discharging will happen in this path, that's why it is called as a pull down network. And from pull up, that output part, okay, so output we have a capacitor that is going to be charged up to the VDD, okay, and that is going to happen from the PMOS circuitry, right? So that's why we am calling it is a PMOS, like a pull up network, okay. So now you're familiar with this thing, what is a CMOS, how it is made up of like pull up network, pull down network, okay. So this is the inverter, okay. So now in the CMOS, just remember this thing to carry out the any functionality of any circuit, okay. So for a PMOS, if I see for a PMOS, so PMOS will become on if you apply logic 0, okay, and it will become off if you apply logic 1. You already familiar with this. Now for NMOS, it will be on if I apply logic 1, and it will be off when I apply logic 0. So you already know this thing. So this is the main point that you should need to keep this point, okay, in your mind. Okay, so now if you see this functionality, okay, so if you see this V in, okay, so we will discuss the functionality later also, the CMOS inverter, so you will understand this thing, right? So now we will, like, I will be discussing some point like how to implement any logic using CMOS. Okay, so let's cover this topic also. So now we will discuss how to implement any logic using CMOS. Okay, so just remember this thing, this point is very important. Okay, so if you are going to construct any logic, okay, so suppose, okay, so just remember this first point. If NMOS is in series, okay, and parallel is our next case. Okay, if NMOS is in series, okay, then in this case, this PMOS, in case of series, it will be in the parallel. Okay, and if suppose NMOS is in parallel, then it should be in series. So this is the first point you should remember. Okay, that if your NMOS is in series, if suppose you have a pull down network, in that you have a NMOS transistor, if that is going to be in series, then we have a pull up network also, just connect that transistor in the parallel fashion. Okay, and if your pull down network is in parallel, then connect that PMOS fashion, okay, that is pull up network, in the series. So just remember this thing. Okay, now second point is this, just remember this thing. Second point, for product function, like suppose if you have A dot B, if you have A dot B, so that NMOS will be in series. So suppose A dot B, you need two NMOS transistor. Okay, so it is going to connect as a series. Okay, and suppose if you have A plus B function, if you have A plus B kind of a function, then in that case it is going to be as a parallel. Okay, I will show you circuitry diagram also, you will understand. Just remember these points. Okay, these are the highlight of this, like this implementing any logic. Okay, then you will not face any issue. Okay, and for the same thing, if you are implementing this AB like a product function using PMOS, then in that case, if suppose NMOS is in series, I already told you in the first point, if it is in series, then in PMOS it will be parallel, so then it will be in the parallel. And if it is in the ORing function, then in this case it is in the series. Okay, just remember these points, these 2 points are very important. Okay, I will show you how you can going to implement any logic using CMOS, okay, in the later part also. Okay, I will cover this part also, so don't worry about this. Okay, so these 2 points you should need to remember. Okay, how you are like going to create any CMOS circuitry if you want to implement any logic. Okay, so just remember this thing. Okay, so these 2 points will help you to make a circuitry diagram. Okay, I will cover this thing also. Okay, so now let me discuss this thing also, that logic 0 and logic 1 concept. Okay, so what is a logic 0? So one thing is logic 0 and another thing is logic 1. Okay, so see, logic 0 doesn't mean like it is a logic 0 means logic 0 volt. Okay, it is a basically it is a kind of a band. Okay, so if you see this thing, okay, so suppose this is a 0 volt, might be it can be 0.8 volt. Okay, here we have another band, it can be like suppose 1.6 volt, and it should be 2 volt. Okay, so this is a band. Okay, if your output is lying in between of this voltage level, if suppose your output is 1.7 volt also, then it means it is a logic high. So this represent logic high. Okay, and if your out like input, like if your input is logic 0, okay, so it should be in the range of 0 to 0.8 volt, and it will be terms at logic 0. So basically it is a kind of band. Okay, so see, I have represent here 0.8 volt, so it is not a fixed value. I'm just explaining you what does it actually means. Okay, so why these kind of a bands? Okay, so basically you have already like know this point, like CMOS have a better noise margin, right? So if suppose noise is going to be added in that case, so it will not treat as a like noise. Okay, so either it will be logic 0 or logic 1. Okay, so noise capability is better in CMOS. Okay, so now you understand this logic 0 and logic 1 concept. So basically it is a kind of a bands. Okay, so logic 0 exactly don't means it is a logic 0 volt, and logic high exactly don't mean it is a 2 volt. Okay, so now these 2 points you just need to remember. Okay, so I have already covered some CMOS important concepts also. So what are the CMOS important concept? That how the NMOS is going to be on, how the PMOS is going to be on. Because if suppose if I randomly draw any circuit, if you apply like inputs A or B like as a 0 0 0 1 1 0 1 1, so then you can directly put at the gate logic 0 and logic 1. Okay, this thing I'm going to explain you in this next next slide with the help of the CMOS inverter, that how the functionality of that CMOS is going to be defined. Okay, so let's see that functionality also.